Hi, this is Rick Theiner, the Technical Program Chair for the AOCS, and thanks so much for joining us for Silicone, Polymers, and Surfactants. Today's webinar is presented by Tony Olenek. And actually, I have to say, I actually met Tony quite a number of years ago when he reached out to me as president of the Society of Cosmetic Chemists and said, hey, let's do some joint meetings so that the AOCS and the SCC could benefit from each other. And got to know Tony through that and found that he is a fantastic guy in addition to having quite a bit of expertise. For example, Tony is currently the principal consultant for Nascent Technologies Corporation, a consulting firm that he founded. And he's got more than 30 years of experience in the cosmetics industry. He helped establish Siltech as an important supplier of novel organo-modified silicones. And he's also an accomplished writer and speaker. In fact, when it comes time for me to look up some things, Silicones for Personal Care is actually a book I commonly use, which he wrote. He has numerous awards for his contributions to personal care. Now, if you have any questions for our presenter during this time, there should be a spot where you can drop down that menu and type your questions in. And at the end of the presentation, Tony will be answering them. Thanks again for joining us. And with that, I'll turn it over to you, Tony.
All right. Hope everybody's doing well today. I'd like to speak today about silicone polymers and surfactants. A topic that we generally wouldn't consider too much in AOCS. I've been a member of AOCS as long as I've been a member of the Society of Cosmetic Chemists, which is about 40 years. And trying to get the two societies to share very different information we have with each other, I think is a good objective for this. And what I'm trying to do here is to use silicone polymers not as replacement for surfactants, but as materials that can be used to modify the properties of the surfactants. So just like you use surfactants to change properties in water, you can go back and use silicones to change properties like surface tension, like wetting, like a variety of other things in both oil-based systems and water-based systems, depending on which silicone you choose. So silicone is sort of the small additive to the surfactant, which will again change properties that the surfactant has by itself. So although that sounds sort of strange, I hope it will make more sense as we start to go through this. Okay, most surfactant chemists know a lot about oil and water and how they interact and what surfactants do to change that. And they're used to dealing with those two phases that are mutually insoluble in each other. What I'm trying to talk a little bit about is siliphilic polymers. These are polymers that are silicone soluble. So silicone, oil, and water don't go into each other, but by changing molecules and making surfactants and other amphiphilic materials from them, you can get materials that do other things. And dimethicone is simply another phase. It's one other oil. It's not soluble in mineral oil or common oils or esters, but it is insoluble in water, which makes it an auxiliary or a modifier of the other systems. We've been doing this since 1996. And in 1996, I was honored to get the AOCS Rosen Award for work that we did in developing these kind of materials and bringing them to commercial fruition. This webinar really is to bring this technology to AOCS and get people to think about, I've got a surfactant system that's doing something in water, but what can I do to the surfactant to change how the whole system works? Okay, I want to go back to Dr. Rosen because he is sort of the guy in surfactants and such a big factor in our society. But surfactants are the substances that go to the surface and they go to the interface and they alter surface tension, alter energies, and do a lot of things when they get there. The term interface relates to a boundary between two immiscible phases. Well, now we have a third one, or we have two different ones. So these ideas that Dr. Rosen proposed and pushed forward and developed so intensively are things that we want to use now on systems that are a little bit more complicated because they have another oil phase in them and another variable. Okay, talk about immiscible phases. What about the other immiscible phases than oil and water? Can addition of low concentration of silicones act as surfactants to alter the surface tension properties, not only of water, but of oil? And obviously the question is yes to that, or I wouldn't be talking about it. If so, what rules apply to these things? Dr. Rosen and many of us at AOCS have done a lot of work over the years in defining what rules apply. From starting out with HLB and now developing other systems that are more beneficial in other areas. There's lots and lots of work being done to understand them. And we're doing some of those same things from the roadmap that we've used for fatty surfactants. So can we benefit from the addition of silicones? I'd like to start with why silicone. The main thing that silicone does is silicone has an extraordinarily low surface tension. So if you go back and look at the surface tension of water, it's about 72 dynes per centimeter. Standard oils are about 32. And why they're 32 is we're seeing primarily methylene groups at the interface, and that's the surface tension you get from them. Silicone, we drop it down to 25. And having 25 as a surface tension will give us some things we can't do with systems that don't have that, and some modifications of things like feel. One of the key examples I can give you to start out with is foaming hydroalcoholic solutions. Hydroalcoholic solutions have become very important these days with viruses, in that we want to put alcohol, foam alcohol, on the skin and use it for sanitizing. It turns out that the surface tension of alcohol and water that we're trying to foam has a lower surface tension than oil does. It's in the high 20s. So you can't really foam these systems with oil-based surfactants, at least not in any way we know of today. You can, in fact, pick out silicone surfactants that will provide a copious foam on top of a 80% alcohol solution. And that's sort of neat and different. And it has to do with modifying the surface tension in ways that we can't do with other surfactants. The only thing that goes further than that is fluorosurfactants, and they have in the area of around 15 dynes per centimeter. But the fluoro compounds are expensive, and fluoro compounds in some of the markets that I'm involved with is not a favored material. Okay, so by adding silicone to other phases, we can lower the surface tension. We can improve the solubility of phases in each other. We can generate gelation by using solid kinds of surfactants. We can change the wetting speeds by picking the right polymer. We can do emulsification, and we can alter emulsion stability. So we've got a parallel universe, if you will, of fatty surfactants and silicone surfactants. But there's an added dimension to the silicone ones in that they act as surfactants both in water and in oils. Okay, I want to talk briefly about silicone homopolymers in oils, because that's a good place to start. So amphiphilic materials are materials that have two groups on the same molecule that in pure form are insoluble in each other. Amphiphilic materials form solutions, if carefully chosen, in solvents. And these are my cellular things. If I come back and I say, if I put sodium lauryl sulfate in water, it first goes to the surface, first lowers the surface tension, then at the critical micelle concentration starts forming self-assembling units. Everybody can understand that and understand why sodium lauryl sulfate is different in how it solubilizes than is sodium chloride, which should have the same concentration top to bottom and left to right. The surfactants we have from silicone are things that will have that kind of surfactant profile, a critical micelle concentration, a lowering of surface tension, and a variety of other things that come from its being a surfactant in the other phases. So we now can look at understanding these things, expanding them from oil and water as the two only groups. And if you go back and look, everyone is in this group, I'm sure, is quite familiar with running surface tension, where you start lowering the surface tension. And in this case, you can see it's from water because of the starting point, till you get to a point where there is a negligible, significant drop past that concentration. And that's the critical micelle concentration. So we're all used to doing this, and I want to expand it a little bit. What about these other phases? If you go back and look at the phases we're listing, oil, water, silicone, and fluoro, putting them together, they'll all separate from each other in the pure form. So we have to start thinking about something that is hydrophobic, is water hating, but can be water hating because it's siliphilic, that is, loves to go in a silicone, or it can be something that is oleophilic, loves to go into oil, and they function very differently in application. If you look at the picture on this slide, you'll see that you have oil, you have silicone fluid, and you have water separated from each other in the three. Fluoro would be the third, but I have not yet dared to try to deal with that yet because of the complications of that. But understanding whether you have hydrophobicity because it's oil soluble or hydrophobicity because it's silicone soluble is hugely important to what we do. And I'll give you a simple but important example. I live in a suburb of Atlanta, and north of here is the US capital for making carpets. And carpets are treated at the end so that they will be resistant to water, they will be resistant to oil. The problem is if we go back and we put oil on top to make them make the fibers hydrophobic and shed oil, we get good shedding of the oil, but if you're at home and spill cooking oil or you spill some other kind of cosmetic material, some kind of other kind of oil onto that carpet, it will spread throughout the carpet and it'll be very difficult to clean. If the hydrophobicity is provided by silicone, which 99% of it in the carpet industry is, that material will shed both the oil and the water. So one, you get rid of, it's both hydrophobic and oleophobic. And that becomes a key functionality. Now, there are many places that this is important in thinking about coatings and inks and fiber lubricants and just about any industrial application you can think of where surfactants are used. Being able to modify where they end up and what they do, I think, is very important. Okay, and why does silicone fluids do the strange things they do? Primarily methyl groups are what you find at the surface, and that's why the surface tension is lower. So the slide to the left shows the methyl groups, the dark carbon in the middle, and then three little white ones off of them, and that's generally what you see. You also see it because silicones, the energy it takes to rotate is very low. So you can get rotation very easily in these products. What I'm showing on the other side of the slide is quartz, which is the starting material, SiO2, to make silicones. And once you go through the process, the first thing is to go to high temperature and use a source of carbon and take the SiO2 and make CO2 and that material that's on the bottom right-hand corner, which is silicon metal. It looks like shiny charcoal, and people in the silicone business are very intimately involved in maximizing the efficiency of that process. Okay, I want to talk a little bit about cyclomethicones and dimethicones, and I want to talk about solubilities because I think it's important. Cyclomethicone is a starting material for many of the things that we make in the silicone world, and silicone fluids are the common homopolymer of silicone. If you look at the structure on the bottom, there are terminal groups and internal groups, and as you vary the value of X, the viscosity and molecular weight will increase. Strangely enough, in the silicone business, we still sell it by viscosity, not by structure. But putting these things together make the polymers that we're used to evaluating. As you start with D5, D5 is very organic soluble, and start building molecular weight, you get to a point where they become less and less oil soluble and more wanting to stick together. So what happens is the macromolecule is in its lowest energy when it's entangled with another rather than in solution or at a surface. Okay, here's the kind of things we're talking about with molecular weights, the N values or the X values as you start building viscosity. You go from a very low viscosity that has better compatibility with organics. And as you start building up molecular weight, the viscosities get higher and higher. And you get to a point where if you look to the right side here, those things don't really want to separate from each other and are hard to spread on the floor or whatever else you're doing. What we generally do when we get somebody comes into the silicone plant to work, we'll ask them to fill up a 5-gallon pail of a very viscous material, which generally takes a long time and generally results with spilling material on the floor because you get involved in something else and don't think about it. But it teaches the lesson that the viscosity changes, and these are all called dimethicone, all called silicone fluid, and they're called the same by us, but they're very different depending on the viscosity. Okay, and here's a graph showing this. Now, if you look at spreadability, a 5-vis fluid is going to spread much, much easier than a 360 vis material. So the spreadability, how it presents to the surface, what it's going to feel like, how it's going to work when you're drawing a product. And you're talking about a static surface tension versus a dynamic. We're making dynamics in almost everything we do. When we paint, we're drawing a film. When we put on a lipstick, we're drawing a wax. So the surface tension and spreadability becomes terribly important in picking the right product. Okay, so here are silicone fluids, the very common ones, 550 and 350, and the number of D units and the viscosity. Okay, I'd like to address for a minute solubility. If you look up information on solubility of silicone fluids in organics, it's going to say they're insoluble. But just like nothing is infinitely soluble or nothing is zero soluble, solubility changes, but we don't necessarily acknowledge it. So I'm going to try if this works. Okay, this is 5-vis fluid, and we're starting to add mineral oil to it. And you can see it's not acting like a normal insoluble material and turning hazy initially. You can actually see it's starting to form assembly units. You can see this globulation occurring. And as you get closer and closer to an endpoint in so many of these things, you actually will take longer to come in. You're starting to see a little bit of haze coming in now. That haze has to do with forming macrostructures that are large enough now to start to interact with light. But I'm trying to show this to say, despite the fact we say it's insoluble, it is actually got some limited solubility in there. In many instances, will change the surface tension and still be homogeneous, even on centrifugation. So this kind of situation where you can go back and add product and watch how it goes in is terribly important when we consider what we put in and what we're trying to accomplish by adding it. If lowering your surface tension is the key of what you're doing rather than subassembled units, you can use silicone fluids in oils at low concentrations. So let me go to the next one. Okay, now I think that's the same one. Hold on, let me try. Oop. Okay, this is really the same situation again, so I'll pop onto the chart at the end. A 5-vis fluid that we just looked at, if we take mineral oil and we put mineral oil in it till it develops a haze, it will take 5.4%. Not a negligible amount when you think about critical micelle concentration. If we go into a more polar oil like sweet almond oil, which is a triglyceride, that number tumbles from 5.4 down to 0.75. If we lower the viscosity to 1 centistove, which is a very small molecule, you can put lots of it into both mineral oil and sweet almond oil. So when I say it's insoluble, it's a material of a certain molecular weight that is insoluble. If I pop up to F10, which is a much more viscous material, we're starting to see some of that interaction, some of that interaction between the molecules where they would rather be associated with themselves than with the solution. And the numbers not only are low, but the sweet almond oil and mineral oil are getting closer and closer, because it's not driven by the solubility of the oil, it's driven by the interaction of the silicone fluid versus going into some kind of subassembled molecule in the organic phase. Okay, so some silicone fluids, we can even use them to act as surfactants in oils. So properly chosen, and anything that would have a CMC below 5, you can go back and put silicone fluids in and look at the efficiency of how much it takes to get to a surface tension of around 25. So we can get 25 to 27, and when you look at it, most people can feel the difference of 2 dynes per centimeter. So these things have very different feels. They also, I would say, have very different spreadability, have different effects on rheology, and are very important to change properties in a whole variety of different areas, including plastics, the flow of plastics, thermoplastics, and the like. And these things are used for that reason. Okay, so silicone fluids have some solubility, albeit very limited in concentration, and viscosity of the silicone fluid chosen will help you maximize the effect in both mineral oils and esters. So this is that determination, that kind of interaction. What do we do with entanglement? If entanglement is highly favored energetically, it'll be predominant. Where that kind of solubilization that takes time is something that will generally take a little longer. You can also go back and look at different viscosities of silicone blended together so that you can look at how they're going to work. And it opens up a whole new area to modify flow and feel and viscosity and a variety of others. Okay, I want to talk a little bit about oil-loving compounds because they're the first of the strange ones I'd like to address. If we go back and look at amphiphilic materials, we know what they're about. We know how to go back and look at hydrophilic and hydrophobic sections. But oil-soluble silicones are things that will lower the surface tension of the oil. Now, ex-silicones and ex-fluoros, that's a pretty good trick. So going back and being able to take your oil and give it a surface tension in the 20s, for spreadability, for any of those other things I've already mentioned, silicone, oil-soluble silicones are very interesting in this, and I'll show you structures in a minute or so. They form gels. If you have silicone, oil-soluble silicone polymers that have alkyl groups on them that are higher in carbon number than 18, you can put them into oils and form solid gels with different rheological properties. Because of that, they change aesthetics and how they feel and how they spread. And you can change the syneresis you're getting. That is the leakage of one oil from a gelled structure by changing the solubilities of each in the other. So these are the structures I'm speaking about now. So these are not homopolymers like before. These are amphiphilic materials where the alkyl chain is soluble in oil, and the A modification is soluble in silicone. And by changing those ratios and changing the length of alkyl, we'll see very different properties. I'm going to take as an example a C16. This is cetyl dimethicone, has a low viscosity, and it is soluble in esters, triglycerides, and oil. It lowers the surface tension to around 25 at a use level about 2%. And it modifies the feel and the flow. Okay, so here's the structure. And there's 2 types I'm looking at, one with a ratio of 1 to 1. Both the material that's silicone soluble and oil soluble are on the molecule at the same stoichiometric coefficient. So A and B are equal to each other. That's generally a good place to start because when the things are most different, we can capitalize on the performance properties. Okay, so the C16 will make things spread better, make it feel more like silicone, and add a silicone feel, particularly as we get the ratio of silicone units higher relative to oil units. Okay, and if I go back and look at cetyl dimethicone added to soybean oil, you can see what looks like a pretty good CMC curve here. You can go back and actually see the surface tension dropping from around 31 point something. And at around 20%, it gets to an area where it starts to level off. It's not as clear as to where the CMC is because it doesn't immediately go parallel to the x-axis. So what we did is we invented a term called refractive RF50, and it's reduction in surface tension to 25 dynes. So we have a number we can read and extrapolate to rather than trying to figure out where that inflection point is. But looking at this, you can go back and imagine, and we can show that it starts going to the surface. You start lowering surface tension, get to a point where the surface is crowded and entanglement enters into it. And then you minimize the further drop in surface tension. And if you call it RF50, it's easy to get a pretty good number. So you can see that we're able to get into 25 fairly easily. Okay, the same thing is true with mineral oil, although the graph doesn't look as good as the last one or as good as a normal CMC would be. But you can see the surface tension starts to drop. And here particularly you need the RF50 because it's almost impossible to find out exactly where that inflection point is on that graph. But going back and looking at the data, you can see that it's about 50% here. Now, these molecules were not optimized in any way. And as you go back and start looking at optimization, those 50% concentrations can drop in some instances to tenths of a percent. So this is the kind of thing we'd like to think about. This looks very common to we that work in the surfactant business, the surface tension dropping, getting to a point where the surface becomes crowded. We start self-assembling, making gels at the critical micelle concentration. In this particular case, is a much more efficient one because we're down around 5%. And still, that is not the most efficient we can be. Okay, so here is what these things look like. You look at a polymer not from the point of view of its gross properties, but looking at the ratio of things to each other. In one instance, you can have a group that has lots and lots of alkyl groups and very few silicone soluble groups. You can go back and change these things in any way you want. And by changing that, you change the properties of the groups. I'll show you that in a second. So alkyl silicone selection rules, are there rules that allow for more efficient selection of alkyl dimethicone, or is it merely crystal ball gazing? Well, if we go back far enough in the history of our surfactants, you could have asked the same question. People who work very hard on understanding this and continue to do so have moved the science very far in terms of our understanding. So if I go back and I look at a variety of C16 products, A through G in the group, I'm changing the amount of alkyl relative to the amount of silicone. And here's the ratio of them, but the percent alkyl becomes a very key factor in what we're trying to do. Excuse me. Okay, so we start to look at these things. If you look at the far left, where the percentage of alkyl is very low, you find things, not surprisingly, that are soluble in silicone fluids. Now, when I say silicone fluid, I'm talking 350, where there starts to be some entanglement. You can generate parallel graphs to this if you want to do it in lower vis fluids, where the concentrations would change relative to what they're soluble in. But we have a section in the graph based upon the percentage of alkyl, which has to do with whether it's silicone soluble, mineral oil soluble, or CH10 triglyceride soluble. So we can add an alkyl silicone and modify the properties of silicone fluids, of mineral oil, and of silicone fluids that are more polar, like CH10 triglycerides. So it opens a whole other way to think about these things as additives to surfactant-based systems to change some of their properties. Okay, so if we start to look at this, this is the full graph of things where we've put everything together. We've talked about what they're soluble in. And we basically find that below a percentage of 20 in weight, you can get solubility in 350 vis. When you start coming up, the next one we did that changed was around 22%. You start finding mineral oil solubility. And as you start going up in alkyl, you get mineral oil and then C8, C10 triglyceride solubility. So these materials will act like the demonstration I showed of adding product to it, that in fact it will become miscible. You'll see things forming when you're doing it, and you'll get more micellar rather than sodium chloride type solubility parameters from it. Okay, so what we did then is we went back and said, okay, we've got these data generated. How applicable are they to other things? So we made up a variety of alkyl silicones after we did the original publication and looked at changing, if we took 16 up to 22, 26, and then actually the 32, but looked at the percent alkyl in the product and found the observed versus the predicted was pretty good. That these things, in fact, are predictable. You can figure out where they're going to go, what they're going to do at the surface by looking at surface tension and other things, and looking at surfactant properties of, in this case, alkyl silicones in oils of different polarity. So it offers you a possibility of formulating products and having properties associated with the surfactant make it easier for you to do it, and change the parameters like surface tension, solubility, and the like. Okay, so as we go back and look at, we wanted to go back and say, okay, what happens when we look at a straight C16 where the alpha olefin is the material up top in the right-hand side, and then the SiH fluid that's used to react is the 100% material. It's only 51.1% alkyl because of the methyls in there. But to go back and look at the surface tensions of these things, you can go back then and do a graph, and you can see the relationship between them. And here's that relationship. So surface tension is in fact related to the amount of alkyl that's on the surface. Now this is a particular model of it. It's cetyl and it's got certain ratios, but there are lines that can be generated for any of the things you're trying to do with the silicone. So if you're trying to take and put an elastomer silicone resin into a system, you would develop a line based on the materials that are most applicable for your application. Okay, so what does this mean commercially? Other than something that I find interesting, what does it do? So we've gone back and we actually looked at taking Mobile 1, synthetic 10W30 oil, and taking one of the acetyl polymers we just discussed, or actually a variety of them. I'll show you a table, but one was particularly good, and adding them together to get a clear material that we'll say is a solution, but it's a solution of surfactant, not of ionic materials. So what we did is we went back and we looked at surface tension. The untreated lube versus two different molecular weight materials, and looked at what it does to surface tension. Untreated materials were around 31 dynes per centimeter. And we, in fact, with additions of either 0.5 or 1%, could drop them down into the 20s, 23.5, 22.5. But we did get to a point where some of them were not soluble. In the case of the 0.5%. So it wasn't soluble, so we couldn't do things with it. But what this is showing is that going back and looking at surface tension and looking at adding silicone in small concentrations will change the surface tension as measured by ASTM D7490. And that thinking of these as additives rather than just surfactants or rather than just as insoluble materials will open up whole wide areas of things we can do. Okay, and here's a graph of conventional oil. And we have a graph of synthetic as well. So these are ester-based products. So specific kinds of materials designed for this application will allow you to get very low surface tensions, which is very hard to do with other things. Okay, US patent 5320761 from Pennzoil actually talks about surface tension reduction as something that you want to get, something that relates to improved fuel economy, and putting it into the oil phase, into the, not the oil phase, but the oil itself. So there is reason to believe that there were positive things that come out of those changes. And in fact, engine studies are being done to verify that. But looking at things like deposits, when it's in the crankcase, you don't put silicone into the combustion engine because you'll mix some silica at the end, which is probably not a good thing to do if you want to keep the car going. So this is the ways that we think we can look at these products in things that we're already doing on industrial applications. Okay, the other thing we can do is as the chain length comes up, the alkyl chain weight comes up, it changes the melt point. So waxes that have alkyl groups from C12 to C16 are liquids at room temperature. Now, remembering that these are not esters, these are made from alpha olefin. They are different in many respects than are the normal esters in the carbon world. At lengths of around 18, they become solid and the melting point increases. Okay, so what we can do is we can actually, by changing the ratio of silicone to alkyl, we can change the hardness, softness of the wax, we can change the rheology of the wax, and we can change a variety of other functions in the wax. So I want to talk a little bit to start out with about a C26 product, which in the inky world, which is different from what most other people want to do, but it's called Serato, has a melt point of 47. It's soluble in esters, triglycerides, and other oils. When I say soluble, again, as a surfactant soluble rather than sodium chloride soluble. Okay, so here's what the molecule looks like. Now we've got a much longer chain. We've got a chain that's going to want to, when it self-assembles, find other related chains and start to solidify and keep the liquid parts of the A units separate and functioning differently, which is what we find. Okay, here's an example of olive oil. What we did is we changed the amount of alkyl. In this case, I called it silicone, 20% silicone, the remainder being alkyl, 40% silicone, the remainder being alkyl at 60 and 80. And we added 5% of those C26 alkyl waxes to the olive oil that's in the upper left-hand corner. And what we found, this is completely thermal. It's not like making an elastomer in there where once you gel it up, you can't go backwards. We can actually warm this up and put it through the phase multiple times. We found materials that will be about clear when you start at lower concentrations of silicone because it's more soluble in the oil. But then you get to a point where at a large silicone concentration, it becomes opaque. Doing this, one of the things we observed in the cosmetic side of it is that the materials that have a low percentage of silicone are oil phases that when they're put on the skin will change transepidermal water loss. They'll prevent the drying of skin. When you start getting to 80% silicone, that property disappears. Because of the high amount of silicone, the films become more permeable, and you actually end up with materials that are breathable, much like contact lenses, which is why we put silicone into those systems. So the ability to change the rheology, to change the viscosity, to change the melt point, and to change permeation of a film that you would make with it by altering the amount of alkyl to silicone, even at low concentrations, I think should offer some excitement to some of the things that we do by putting these surface active kind of materials into formulations in the oil phase, or as I'll show in a minute or two, in the water phase. I think this is an interesting This is a surfactant of a surfactant, and I think is really a very difficult way to think about it initially. When I first asked the question, what is the critical micelle concentration of acetyl dimethicone in olive oil? I say, no, wait a minute, that doesn't make sense. How can that happen? But in reality, that's a legitimate question. What we also can do in this particular case, we have a product that has very large amount of silicone and very little alkyl, so I'm gelling 50 vis fluid. So in order to look at these things, what we're going to do is how effective is the gel. We'd go back and actually make up the concentrations and turn them upside down, and the next day come back and look at them. The ones that are not legitimate gels will be 0 and 10 where they drop, starting at probably around 15, but in this test, you can see 20 as a starting point. You can see these materials, at least over time, the gel doesn't degrade to a point that it falls. And you can look at them and see very different flow properties, very different other applications parameters that you can get from using an alkyl silicone to gel silicone fluid. Okay, so when we go back and look at the surface tensions of these things again, we can find that there is a very good correlation between surface tension, regardless of what the alkyl chain is within reason, that we can predict and match surface tensions decently. So we can go back and pick a material that's going to be either lubricating like a 16 where it's liquid, a soft solid like a 22, or a hard solid like a 26, and determine what kind of parameters we're going to get when we put them into the application, when we put them into the oil systems we're looking at. And I think that's very exciting. I think that's some interesting stuff. Okay, so we're adding a C22 alkyl silicone, 10% by weight. In this case, it's the alkyl silicone alone, it's the mineral oil and sweet almond oil, where we can go back and from a top view and a side view, see in many of these instances, depending on what the oil is, you'll get different parameters from them. The mineral oil is almost clear, but if you go and both from the top and from the side, it is a gel. The sweet almond oil is more opaque, but is also a good gel. And the alkyl silicone is itself a gel. So you can change these properties and use these for gelation, use them for surface tension reduction. And by changing the concentration, you can get better gelation depending on what oils you're using. So there's a lot of variability in how you formulate. Okay, so here's a C26, and you can see, certainly from the right side, the second one particularly, that these are much harder. They're higher melt points. They're in the 50s rather than in the 30s. They're clear in some systems. Where you go over to the sweet almond oil, a more polar system, they are not clear, but they still have nice rheology and still nice feels to them. So what you're doing with them and where they're going have a lot to do with what kind of properties you're going to get from them. Okay, having thrown the ideas of using alkyl, first silicone homopolymers, that is silicone fluids, as materials to modify the surfactant properties of a surfactant that goes into an oil, I think is a very, very interesting concept. We can change the feel for sure, which in the cosmetic business is very important, but it also carries over into areas that are not personal care, but are industrial, as the motor oil and as some of the other things. So going then to the things that go into oil, which by putting alkyl groups on, we can get analogous kind of performance. And now I want to talk about putting water-soluble groups on and what that's going to do. Okay, so the materials that I'm talking about are PEG dimethicones. Again, INCI is not IUPAC and is not put together to help you really understand what the structure is, but to put a label on the back that the consumer can read and understand some really basic stuff. But one of the things I want to point out is not to make the mistake that silicone surfactants are always low surface tension. A silicone surfactant that has a lot of EO and PO on it will actually get to a point where all that's seen at the surface is the EO and PO, and it will act in terms of its surface performance like a regular ethoxylate. In the case of what I'm showing here, we have 8 moles of PEG, 0 moles of PPG, and we can get the surface tension down to about 25.3. If we go 18 moles PEG and 6 moles PPG, we're now moving it, and it's moving closer to where the surface tension would be for primarily a almost all EO-PO kind of product. Next one is 16, where we're up around 32, which is the surface tension you'd expect for an oil phase. So you have to try them. You can't go back and get something off the shelf and say, what is this? Well, it's got this inky name. Go ahead and try it in motor oil. If the A to B ratio is wrong, which doesn't show up in it at all, the whole parameters fall out. If I have 1,000 Bs and 1 A, it's going to act as if it's going to be silicone soluble, as if the A is negligible on many of the molecules, which it will be. So formula structure is terribly important. Okay, so one of the things we wanted to do is everybody loves microemulsions. Microemulsions because of their stability, because of some of the properties that they bring to emulsions in terms of easier to use and a variety of other things. We went back and varied the A to B ratio in a PEG 8 kind of product to look at what we actually got when we put them into water at to see whether or not it was going to be soluble, insoluble, or a microemulsion. And there are a number of formulas in here that you can go back and see that we have the insoluble, we have the soluble, but really interestingly is we have the microemulsions. And if we go back and look at the ratio of microemulsion of the A to B and go back and plot it, we can see we actually get, in this particular type of system, we can actually get a reasonably good line. So these things are predictable. If I have a product that I want to get a silicone to help in stabilizing a microemulsion, I can go back and actually pick from this chart the ones that will help in what you're looking for. So this is something that you can go back and by adding a silicone system in, you make more complicated micelles and more complicated surface assembly things in it than you would normally get. And it does give some very nice improvement to microemulsions. It's 1 or 2 systems that we really looked at intensively, but looking at it and understanding the materials that go into your formulation, you can pick the additives that will be most helpful. Okay, so there's a simple rule that comes out of it, going back and looking at a formula by reducing it from the graph. You can determine the amount of B units and A units, that's the silicone soluble versus the water soluble, for an 8 mole PEG type of product. You could do it for other things as well, but the formula would be different. Okay, so we go back and we look at the wetting speeds and surface tensions of things. This is a PEG 8 dimethicone. The structure's there. The ratio of A to B is 1 to 2. So we're looking basically at systems where we have a 4 and an 8 for A and B respectively. If we go back and look at these things, and the graph below I find very interesting, is what it basically will say is you get pretty good wetting. And by wetting, I mean Draves wetting, not super wetting that you find in ag products, till you get to a certain molecular weight, and then all of a sudden that graph just sort of takes off in a hurry. It sounds surprising after we did it, but as you think about it, it makes sense. You get to a point where larger molecules are less capable of getting to the surface, get more entangled with each other, and as you put them in formulations, get more entangled with other surfactants, that once you get to a certain size, entanglement becomes the driving force rather than getting to the surface for wetting time. But to start out with, you get some really good wettings. You know, you're looking 7, 8, 10 seconds as you build the molecular weights up. Finally, when you get to a point that you've got 10 times the molecular weight of the 632 roughly. R7 then becomes 88. So the wetting time is definitely related. Now, molecular weight as well as ratio of A to B are things that you have to know before you start formulating, before you start putting products and systems together, because that's really what's driving these things. Looking at the surface tension, you end up with the molecular weight as it gets higher and higher, less of it gets to the surface. You see less of the lowering of the surface tension, but you can start out around 22, which is a good place to start foaming hydroalcoholic solutions, up to 23, and then keep going all the way up to 30.8, which is minimal silicone participation in the product in terms of surface tension and wetting. Okay, so if we look at these and we go out and you can actually graph it, go back and look at the ratio of a particular PEG dimethicone or a particular alkyl or a particular whatever else. While I'm talking about wetting times here, I'm talking about wetting times in water. We have wetting times in oil we can change. By using these materials and changing the surface tension instead of from 72 down, starting at 32 and going into the 20s, we can change the wetting time to drop a fiber into an oil. And those kinds of abilities, I think, are really interesting. The wetting of metal in a potential motor oil application. All of these are done by just changing which phases are which and going back and picking the molecule that you want to look at to optimize for that kind of performance. Okay, I think I've thrown a tremendous amount at you at one time. I'd like to get, as a conclusion though, to get you to start thinking about insolubility. Does it really exist? I don't think you'll find anything in a partition coefficient that's absolutely zero, or anything that's infinitely soluble. So as you start thinking about that, give some more thought to things that are active at the surface, and maybe not being soluble is a good thing, because you want to get them to where they can perform. The second thing is there are 4 phases that are mutually immiscible, and all the things we do with the 2 we're used to dealing with are equally as plausible and equally as interesting when you do them with the combination of the others. So I showed a few of them. There are a lot more you can think of, so that you can get the expensive actives that you want, or the silicone surfactants, which are generally more expensive than oil surfactants, to the surface to make up a smaller portion of what you're putting in there to get the property. I like to say, if you think about silicone surfactants as something that you would, a spice that you put in a gourmet meal, they'll never be the majority of the formula in most of the things we deal with, because they're too expensive or because there's other solubility or other parameters that are difficult to control. But as minor additives, we can get improvement in performance of the formula simply by going back and looking at how these things go in, that they're soluble in a surfactant way, not in a salt way. Hopefully with that, it made some kind of sense as to what we're trying to do. And I thank you for listening.
Well, thank you, Tony. That was, you're right, that was a lot of information, and it was excellent. That was really great. We have some questions, and I believe we've got some time so that we can put them to you. Sure. And the very first one is actually, it's a question about where we stand on the consumption of the different silicone types of products. F350, for example, is approved for edible oils, but what about other types of materials?
Edible oils, the F350, you're absolutely right. F350 is the FDA approved material, but it's approved as an over-the-counter drug. So other materials can be added that are, for example, if you put a 50 vis fluid into a barrier cream or into an oil or into something else, I guess it probably wouldn't work that way. Let me think this through a little bit, because it's a different, I hadn't thought about this question before. In the cosmetic side, you can add things that are not functional materials. And I think in the food side, you can add things that have other properties like defoaming and whatnot. The honest answer is I hadn't thought about it, so I'm really not an expert in that area. So I don't want to mislead you. I think food, it's processing of oils, perhaps it would go into. Silicones are used commonly right now in, I know it's not the same, but it's analogous. Oil that goes into a pipeline, crude oil, has a small amount of low vis fluid put in it so that you can get laminar rather than turbulent flow. And it comes out during the time that the treatments are done. So I wouldn't think that in and of themselves, the food grade, there might be other food grade applications. Some of the water soluble materials are used as emulsifiers in ice cream. So they probably are usable. It's going to take time to go back and look at them. And also you need to know under what section of the code they need to be approved. You know, we have a lot of things that go into contact with food when they're applied to a wrap or some kind of plastic of something that like saran wrap that are different than when they're actually added to a food. So the actual honest question is I don't know, but it's going to be an interesting thing to look at, and I certainly will get started in looking at it.
All right. Well, let me well, there's another question which is a bit different than that one, and that is, what's the critical molecular weight where entanglement becomes important in silicones? And this came in early, so I think that was particularly talking about when adding the silicones to oils.
350 for sure is a tough spot. 50 is about where it starts to change. 50 vis fluid, and the molecular weight I have here somewhere. It's on one of the slides. That's when entanglement becomes, the important issue. Entanglement actually is it's easier to run the little test with the mixer I just showed to look for entanglement than it is perhaps in other ways to evaluate it. But 50, this is where it starts. By the time you get to 350, you have horrible insolubility. And that's why you'll see in all of the things we're doing, we show 350 as where it becomes the insoluble material. But even that is not zero.
All right. As you were saying earlier, yeah. So, and a question from me actually is, the PEG dimethicones that you were talking about, for example, with the 8 PEG 8, are those discrete? Are they always going to be 8 EEOs on those alkyl units, or rather ether units, or is there a variance?
Yeah, that's the beauty of being a surfactant chemist coming from the standard side. There's an oligomer distribution of the ethoxylate, and there's a oligomer distribution of the polymer. Not so much for the alpha olefin because that's much more carefully controlled, but it is a Gaussian curve that you'll see, and it is an oligomer distribution for sure. And that is another interesting thing is people actually blend things that are very different to make bimodal materials, where one may be in there for wetting and
just
the other
like in our world.
Exactly. The things that there, the formula you'll use to evaluate where it's going to be soluble, the numbers are going to be different, but the concept is exactly identical.
Gotcha. All right. Well, Tony, thank you very much. It's noon, and I'm afraid that we're going to get kicked off.
One more quick comment though. There's at the last slide that's up. There's the book, the Silicone for Personal Care book, is available from AOCS. It's in the library. So if you'd like a copy, if you get a PDF, you're more than welcome to download it. And there's more information on each of these topics.
And this is Amy, I put a link to the book and the confirmation email that you will receive tomorrow with the recording.
Awesome. Well, again, Tony, thank you so much for this excellent presentation. And I will also say thanks to our attendees for showing up.
Thank you all for coming.